extend or maybe go one step back, or you can put it whatever, however you want, to what Ina just explained, the nature-based solutions. We saw they are wonderful, they look nice, they are useful, but let's try to see how we can employ them, nature-based solutions, to actually solve some circularity aspect. So I will add another term in today's session. I need to ask you first, do you see your what do you see on the screen? Do you see only the presentation, or do you see yourselves also? Just the presentation. Okay, so I can keep your figures here on this screen. Right, your picture, sorry. So basically, I would like to add one more term to nature-based solutions, and this term is circularity. And we are focusing on cities. What does it mean, circularity? It simply means that we focus a little bit more on the resources that we are using, because the major goal of what we want to achieve is to manage our resources in a way so that the cities don't impose burden to the environment. But let's see first why. So this is the outline of my talk. I would like to first explain why actually are we focusing on cities and urban planning and managing of resources. Why cities? Then I would like to just show you a little bit. As I said, I don't know exactly your background, so it's maybe somebody will already know about this quantification, somebody not, but I'm sure you will all be able to follow. So let's quantify these resources a little bit. So to see what are the basics to design these nature-based solutions and why, and then we will turn to circular management of resources. We will see what is that, and I will present you a framework how to implement nature-based solutions in relation to the EdiCitNet project that Ina also mentioned. So cities. Cities are very interesting things, but basically cities started appearing when we managed to produce a surplus of resources. So basically they are dependent on resources, and cities are basically a community of there are places that are sustaining permanent population, okay, but based on resources. So if somebody can produce surplus of resources, which is crop yields, then we can sustain the cities. They depend on resources. And one more, and this milestone happened, do you know when? It happened basically 10,000 years before Christ. So when the agriculture appeared. So then people started grouping in so-called cities at that time. But the other milestone that really enabled the cities to grow in population is water supply techniques. It's water supply engineering. So the ancient Rome, when they figured out how to bring water from one place to another so that people don't need to live really close to the water, then Rome, the ancient Rome, expanded to 500,000 inhabitants. And you know what happened in the Dark Ages. All this engineering knowledge went down, was not there to sustain these systems, these water systems, and the ancient Rome then declined, the population declined to 30,000 inhabitants. So this is directly linked to this engineering knowledge of water supply. And then the other milestone that really enabled the cities to grow or stimulated the urban growth was Industrial Revolution. So the cities just started expanding. Well, cities, since then, cities have become really the center of economic development, of productivity, of innovation, and so on. And globally, we know that they account for more than 50% of the world population, and they account for 80% of economic activities. So they are important formations. And this is an interesting chart here. That you can see, this is basically from a web page called Our World Data, and you can see the population growth. So here are some countries, but you can actually, if you go to this page, this is supposed to work live, but it's not working here. Well, doesn't matter. But anyway, what you can see here, for example, the world went to 50%, and China, for example, went to more than 60% in 2020. Brazil, urban population in Brazil is more than 80%. So this is quite worrying. And why is this important for us? It's important because the major demand for resources comes from cities. And if I know how to manage these resources so that they are not depleted and I'm not producing waste, then it's very nice. So I just need to manage the cities in a circular way and it's fine. Well, it's easier said than done, but let's see what can we do. Even if we say the major demand for water comes from agriculture, right? Well, but the demand for agricultural products comes from cities. So this is a fact. And the resources that we are talking about are renewable or non-renewable. So renewable resources are water, soil, plants, biomass, animals. All this is coming to the city. And non-renewable, mostly related to energy, gas, oil, coal, and minerals. Don't forget about phosphorus. It's non-renewable resource and one of the most important fertilizers. But please be aware that renewable resources are renewable as long as we are using them in a sustainable way, so that we allow them for them to renew. If we are using water too much, then of course it will not be able to renew. This is a very nice example is groundwater. You can only extract groundwater as much as it is renewed by precipitation. If you go deeper to the groundwater, then of course it will not be renewable anymore and you will stay without water. And not to explain too much, because you probably know these things, we live in exponential growth. Still, unfortunately, in spite of all regulations and green deals and whatever, we still grow exponentially in our demands. So here you can see the water demand grows exponentially still, and fertilizers, they grow exponentially. So this is the world here, China, but basically the global growth for fertilizer means that the demand is too high. So, oh, I'm sorry, I went to the end. Okay, let's go back. So, I'm sorry for this. And then another thing that I would like to mention is how we manage our resources. Just simply, we are not managing them efficiently, particularly when it comes to water, because climate change is coming to us in a very bad way with droughts and floods. And with nature-based solutions, we can mitigate these things for sure, as you will see later on in the presentation. Droughts are nothing new. Basically, somebody, we have students from Italy as well, and you know lately that in the Po River Valley, there was restriction to water use already now in June. And then on the other hand, we have floods. And these are the extreme events that are coming with climate change. So the urban metabolism, finally, what cities do with the resources and what can we do about it? That's more important. What cities do, urban metabolism is quite complex thing, and it requires really knowledge, really interdisciplinary knowledge in energy, in water, in biomass, and so on. But generally, cities receive water, mostly drinking water and rainwater that falls to the city. They receive biomass in terms of food and other material. They receive gas, oil, coal, and also some renewable energy from wind, sun, wood. Of course, materials which are degradable, non-degradable, minerals, different minerals, including fertilizers. So all these resources, they come to the city, and what the city does, we use them, okay? We eat the food, but then we flush it away with wastewater. So the city, on the other hand, it produces wastewater, but when we talk about wastewater, we need to talk about what's in the wastewater. We have organic matter, we have nutrients and water, of course. Then the other thing that comes from wastewater is solid organic waste, but we also have some micropollutants that are making our lives quite complicated. Then from these materials, what comes out also is organic waste. Then we have from the energy, we have emissions to air, CO2 and other greenhouse gases, and then we have other waste that ends up in landfills, like plastic, paper, glass, and other material. So this is, in short, linear urban metabolism. And I dare to say most of the cities globally still live in this way. So the problem, if I go back to the beginning, the problem with cities is that they import a lot of resources, but then on the other hand, and this is the problem of resources depletion. We are running out of resources, but the other problem is producing waste. And this waste is actually destroying our natural environment that, on the other hand, are producing these resources for us. So basically, if I try not to produce, if I try to use these resources in a cycle, then I can save the resources and I can prevent producing waste. So you have two sides. So before we go to these circular concepts, let's try to quantify some resources. Again, I think it's important to know a little bit the numbers. So since I'm coming from the water world, let's try to quantify a little bit the water fluxes in the city. So one person needs, let's say, 120 to 200 liters per day. So imagine mega cities will need a lot of water resources. European average or EU average is 130 liters per day per person. And then on the other hand, this same person produces almost the same amount of wastewater, okay, produces this much water, but then in this water, you can find, so I'm not sure how many of you are familiar with BOD and COD, but this is biochemical oxygen demand and chemical oxygen demand. And this is a proxy to measure how much organic matter you have in the water. So it's a measure like a meter or centimeter or whatever. So 5 to 50 grams of biochemical oxygen demand per day per person. Then one person produces 2 to 15 grams of nitrogen per day, which ends up in the wastewater. A person produces 1 to 5 grams of phosphorus per day and 1 to 3 grams of potassium per day. So it looks like, well, wastewater is not such a bad thing, but if you, because these are all fertilizers basically, but if you release, but what do we do with these things? Well, with these things, we take the wastewater to a wastewater treatment plant and we treat them, we remove them. Why? Because if we release them to the aquatic environment directly, they will cause, somebody knows what they will cause to the aquatic environment, the nutrients? Is somebody familiar with this fate of pollutants or
eutrophication?
Exactly. So they will cause eutrophication, and in other words, it means that degradation of the quality of the water quality of the natural water systems, which in other maybe in some cases they provide drinking water on the other hand. So we have legislation for that, and we have to treat them and invest energy in wastewater treatment plants to treat these nutrients. So this is one aspect. So basically we export water, nutrients, organic matter, and other materials. But if we have a look a little bit more in the wastewater, basically what I just said is wastewater as a whole when you flush the toilet. But you can separate these fluxes, and if you separate, for example, the water from the shower and from the washing basins, you will have much less nutrients in this fraction of the wastewater. And then you can also separate the water from the toilets. And in the urine, you will find most of the nutrients. So this actually implies that if I manage to separate urine, I will separate all the nutrients and I can reuse them for whatever I need for agriculture, for example. But this is just as an idea. Wastewater can be mixed, but then, of course, we have different fraction of wastewater, and there are some approaches to use it. Now, another flux of the water that we need to also quantify is rainwater. And rainwater, basically, if you are in a natural environment, the rainwater goes under several processes, and it actually powers the natural water cycle. Now, what is important here, and in the natural water cycle, most of the rainwater goes to infiltration. 80% of the rainwater infiltrates, and this is how the natural water cycle with these processes function. But what does urbanization cause? Most of with impervious areas, we prevent infiltration. We prevent one of the most important processes in the natural water cycle. And if you remember what Ina was explaining with these nature-based solutions for rainwater management is exactly that, to stimulate infiltration and to restore the natural water cycle, to recharge groundwater, and so on. So quantification of these processes, of the fluxes, mostly results in estimating the amount of surface runoff. And based on that, what we usually do in water management, we drain this surface runoff. Why? Because we want to prevent floods. Okay, if we let the water just run on all the areas in the city, we will have floods. So what we do in our linear systems is we do urban drainage, and we have some systems where we put all the water in the same system, so which is called combined sewer system, to prevent floods, but also to take the wastewater away to prevent diseases. This is what we do. normally. So, but then you have also separate sewer systems where you take the wastewater in a separate system and you take stormwater in another system. And then we have nature-based solutions where you take rainwater at the source and you try to infiltrate it, you try to retain it, and so on. Now let's go a little bit to the food, because these two fluxes are very much related. What are the food fluxes? We know that when the food comes to the city, it already has a lot of energy and resources used. And to produce food, we need water, we need fertilizers, nitrogen, phosphorus, potassium that come from who knows where. But then this food, well, we have some yield, okay, and we have some energy value of this food. All this energy value satisfies the needs of the population, and then this population what is the food, and then release the food back to the environment through the wastewater mostly, but we have also some organic waste and wasted food. So we have some data here, how much nutrient is needed per kilogram yield of potato, tomato, lettuce, let's say, for example. We have some numbers here, and how much water is needed can be estimated from other data, from evapotranspiration data, but let's not go. I think we will not have time for so many details. But what I would like you to understand now is how these fluxes of water, wastewater, and food can be quantified, and to see what we have in these fluxes. So this is a little example. So run your calculators, and please tell me. So we have this data we have here that you can use, and I give you 3 to 5 minutes to tell me, if I have 150 people, how much cubic meters of wastewater can I expect? Of course, these are a range of values. Just take one number of this range, for example. How much nitrogen I can expect from this population, how much phosphorus. And then I will suppose that I irrigate a plot of 1,000 square meters with this same water. And on this plot, I can produce roughly 4,000 kilograms, 4 tons of vegetables, tomatoes, for example. And can this production be satisfied with the resources that I have in my wastewater, or I need to go and mine phosphorus from Morocco, for example? Okay, 3 to 5 minutes.
Everyone, okay? Did you understand? 150, no? People?
150 people, you have 120 to 200 liters per day. So how many cubic meters of wastewater I can expect? How much nitrogen? So you have it here, nitrogen. You can take maybe 10 grams, and you can take maybe 3 grams of phosphorus per day and 3 grams of potassium per day per person. So then we will see the results and see what we have actually. And this is something that takes us to a little bit to this circular metabolism. Somebody, it's enough to have 1 or 2 numbers because I have the results on the next slide.
Okay. Some volunteer?
It's just to employ your brains a little bit. How much water do we have?
I found 605
Maybe 6,000.
6,000.
Yeah. Okay, and how much nitrogen? Did you calculate the nitrogen for 150 people?
Not in kilogram. I found it on gram as well.
Okay.
109.
Okay, can be.
In the year for 150
Okay.
people.
Per year. Then, okay, we have to also pay attention that the growing season is just 4 months, for example, or something like that. And so we have to calculate it for this amount of time. But well, let's see the results. But you get the idea. So this is, I mean, we have different numbers here probably because we have a range. So somebody took 120, somebody took 150. But how do you know for sure? Well, if you have measurements, and this is something that we are always missing in design practices. But anyway, so we have this 150 inhabitants produce this much water, which is more than enough for 1,000 square meters irrigation, more than enough. Then we have 650 kilograms of nitrogen, but it's actually 180 kilograms of nitrogen per growing season if the growing season is, let's say, 4 months. And we have then 54 kilograms of phosphorus per growing season and 54 kilograms of potassium. On the other hand, I can, if I produce my 4 tons of tomatoes, they will require only 15 kilograms of nitrogen, and they will require 2 kilograms of phosphorus and 14 kilograms of, oh, sorry, this is a bit less. This is probably around 2 kilograms of potassium per growing season. So I have surplus of nutrients, which means why are we complicating our lives and importing fertilizer? And now we are in fertilizer crisis. Now reuse of wastewater is becoming hot topic with the war in Ukraine because a lot of fertilizers were coming from there. So this is becoming now of a high concern. But okay, things are not so easy in reuse because these systems, I mean, there are some challenges. Technically, it's doable, it's absolutely doable, but there are some challenges. Mostly because, well, the wastewater is diluted and we don't have the nutrients exactly when we need them and in the proportion like we need them. So we need to apply some techniques, technologies on how properly to reuse and to extract these nutrients from wastewater, but it's totally doable. So there are technical challenges to properly do this, but at the conceptual level, we know that we can do it. And if we know how much impact does the phosphorus mining have, then of course it's the way to go. And this is kind of a taste of circular economy, if you want. But moreover, it's because we are using these things today in a very strange way. So basically we have here the city, we are importing nutrients at the high ecological footprints because producing fertilizers requires a lot of energy. And then on the other hand, we have them in the wastewater. To remove 1 kilogram of nitrogen from wastewater in this aeration process, it requires 45 megajoules of energy. in average. But then on the other hand, you know that ammonia fertilizer is produced in the Haber-Bosch process. It's energy intensive process where you produce ammonia from nitrogen from the air. And for this process, you need 35 to 50 megajoules for 1 kilogram. So here you are spending these megajoules to remove nitrogen, and here you are spending these megajoules to produce it from the air. So it doesn't make much sense. So that's why reusing nutrients that we have discharged with wastewater, it makes a lot of sense. But this is how we are living today. This is what we are doing. And as a result of these systems, we have agriculture that produces more than 30% of the entire greenhouse gases, including animal farming. Production of phosphorus, as I mentioned, you are producing ammonia from nitrogen from the air, but phosphorus is a rock, okay? You have to mine it, you have to extract it, and which means it's non-renewable resource. And if we continue like this, it's very likely that we will run out of phosphorus, and there is no life, no plants without phosphorus. There is no agriculture without phosphorus. And on top of that, while mining phosphorus, you are discharging a lot of heavy metals and radioactive compounds. So it has high impact. Then we have plenty of agrochemicals, and we have eutrophication, as you already mentioned, because of agriculture and so on. So many problems. So it's about time to wake up and start doing some different things. And let's go now towards circular management of resources. And we are talking about cities again. So the alternative is to move towards the concept of circular cities. Of course, we can never close the cycles completely. To have a city that is completely using everything in a cycle, that's a utopian city. But we can go a little, we have plenty of reserves to go a little bit in this direction. So a circular city means that you are using these resources, something like we went through this exercise. But this was just water and food. Now we have materials, we have energy, we have minerals also to consider. And we came up in another project, which is called, in a cost action called Circular City. We have identified 7 urban circularity challenges. And these circularity challenges are basically this. So the first one is how to restore and maintain the water cycle by introducing more nature-based solutions and so on. How to manage water and waste treatment, how to recover and to reuse, how to impose these concepts in the city. The third challenge is nutrient recovery and reuse. The fourth challenge is material recovery and reuse. The fifth is food and biomass production within the city. The sixth is energy efficiency and recovery. And the seventh is building system recovery. So you can find more about this in this paper, and you can download it yourselves, or Antonina, maybe you can put it in the materials. So nature-based solutions are actually one of the solutions that can really facilitate these transitions, because by their definition, they provide solution to a specific technical problem like wastewater treatment or urban drainage, by employing natural processes, by bringing nature in the city. So you're solving basically more problems at the same time. And while providing this, as I said, this technical solution, they simultaneously renature city. And they provide many co-benefits. So it's not necessary to use nature-based solutions to provide circularity, but they are really one of the solutions that can really facilitate this circularity and bring many co-benefits in the city. So for example, if you want to manage water in a circular city, so if you live in a circular city, the water management would have two basic points. First of all, rainwater is not drained to the sewer, but is kept on site, it is infiltrated, it is used to water green areas, and we don't consider wastewater anymore, but we have water with resources that we need to recover and reuse. How to put nature-based solutions in a circular context? So nature-based solutions, these are basically solutions that are composed of smaller units. Just to conceptualize better the problem, we define the so-called NBS units, and then we classify these units. But basically, if you want to provide the whole solution, you need to combine more units between each other. So these are the challenges that these nature-based solutions can address, and this is what you actually need to think about. First of all, you need to think about how do you collect your resources, what do you do with the used resources, with the wastewater, with the materials. Then you need to think about nature-based solution systems, how you can recover these resources, and then you need to think, what do you do with these resources back to the city? So the city is considered as a source and a sink of these resources. Everything needs to be safe. So here in this reading, you can read more about the definition in the appendices. You can read about the definition of these challenges. They are better explained what is meant. And within this project, we made a nice film about how nature-based, how circular city should look like. And I'll just play this video and then we continue.
Imagine you enjoy nature, clean air, fresh local food, and beautiful green sceneries in the middle of the city. Imagine cities not just as economic centers, but also as resilient and enjoyable places with nature all around us. Sounds unrealistic and too good to be true? It's closer than you think. The Cost Action Circular City connects scientists and practitioners all over the world to work together on circular cities and bundle their research and experiences. In circular cities, buildings become much more than places to work or live in. Houses no longer just consume. There is a give and take with the surrounding environment. Through nature-based solutions, they store energy and provide high-quality surface water and nutrients, collected and filtered with plant technology directly from our waste streams, monitored for safe use. For all kinds of integrated food productions, like the edible walls or vertical farming, rooftop gardens, mushrooms harvested in our cellars, up to fish breeding in aquaponics. Circular houses include deconstructible joints and incorporate natural materials, like wood or straw and wool in walls and roofs. They contribute to biodiversity and create beneficial microclimates that prevent heat islands, droughts, and floods. Urban farming thrives through community and school gardens. Public spaces become lively areas where water and plants create a fresh climate, even in summer heat, and nature-based solutions absorb stormwater and find CO2. Involving a large number of stakeholders and their interests, Cost Action's Circular Cities combines the superpower of nature-based solutions in a holistic urban web to create a multi-scale network of urban blue-green infrastructures. Benefits are not just ecological, but also economical and social. This Cost Action gathers experts all over the world with the knowledge, expertise, and tools to support you in your communication, planning, designing, and assessing of circular cities. We present sound solutions to the decision makers and implementers so that we can start building the cities of tomorrow today.
Okay, so that's basically in short what we want to do actually. But as I said,
contact us now.
Sorry. As I said, this is not easy. I mean, it's really, the concept is very nice, but to implement this concept, there are a lot of challenges, and you will probably experience some of this during this course, and particularly next week when you will try to solve this problem. But to come back to the content, so the grouping of this system, of these nature-based solutions, and this is all done with the intention to facilitate the design, okay? To facilitate the design. And what we did with these nature-based solution units, we classified them into units, which are technological units, like swales that we already saw and so on. Then we have interventions, and then we have also supporting units. Why supporting units? Because it's very difficult to solve a problem, let's say environmental problem in the city, completely with nature-based solutions. I dare to say it's impossible, because there is simply, the load is too high, and even if you do constructed wetland, you need a settler before that, and this is not nature-based solution. So that's why, according to the definition in this cost action, a nature-based solution, it's not only is composed also by supportive units that help the nature-based solution to function. So you have nature-based solutions for rainwater units, for rainwater management, for vertical greening systems, remediation, treatment and recovery, river restoration, soil and water bioengineering, public green space, and food and biomass production. Of course, one unit can serve to more categories. Like green wall can be also used for rainwater management, for example, but we put it here. As I said, it's just a conceptual approach to facilitate the design of nature-based solution. And here we can see this table. Please go to table A2 of this paper, and you can find a short description with more literature about each one of these units. So, for example, in rainwater management, you have infiltration basin, infiltration trench, filter strips, and so on. And in this table, you can find short description and where you can find more about it. Food and biomass, you have also aquaculture, organoponics, and so on. So all these are kind of classified units. And here are some pictures about nature-based solutions, but already Ina showed you many nice pictures. These are from Slovenia, the three of these pictures. So this is infiltration basin for the parking space. This here is a bioretention cell. And here, this is basically a new urban development in Ljubljana, and I was very happy to see that the rainwater is retained around here. It's not drained to the sewage system, which is actually kind of advancement in the rainwater management in Ljubljana, what I can say. So then we have different vertical greening systems, but if we talk about circularity, I would like to point on something. There are green walls and there are green walls. Some of them are beautiful, but their only function is to be beautiful. And they are even watered by water from the tap. So in a circular city, we try to avoid this, and we try to use at least rainwater to water these facades. But the other benefit that this facade is bringing is energy efficiency. So yeah, so for example, this green wall that you see here is treating gray water. So at the same time that provides all this good look and so on, it treats gray water. And then the treated water, which is collected here, it can be reused for irrigation, for toilet flushing, and so on. This wall here also is beautiful, but it's irrigated with, I'm not sure. Actually, Antonina, we went together to this center and we saw this green wall. And I think it's irrigated by tap water, not even with rainwater. So that's really the difference in the design. And when you will be designing your problems, please think about this. The nature-based solution should be multifunctional, and that's why you will have different experts. So this is remediation, treatment, and recovery. Here you see a nice treatment wetland, which is based on willows. And you can use the willows as a biomass because they really grow fast. And this here is a result of a supportive unit. And this is phosphorus precipitated from wastewater or from urine even. So this is the supportive unit. And then I can use this phosphorus to fertilize my garden, for example. And the garden is nature-based solution. So you see, this is the connection between these supportive units. And what you see here is a raceway pond for algae for treating wastewater. Some more food and biomass. What you see here, this is Andernach. It's one of the cities in the EdiCitNet. It's a really nice city that has urban agriculture really as a top priority. And you basically walk around the city and there is plenty of productive landscapes. But these are gardens. Then you have hydroponic systems, and this is a part of aquaponic systems. I don't want to be too long. Now let's go a little bit to the design. So as I mentioned, in that table in the literature, you can find a lot of, you can find the description of all these units, and you can learn a little bit from that when you will be working on your cases. I would like to tell you a little bit more about the design of nature-based solutions. So the first thing is you cannot do it alone. So don't try. Even if you are a hardcore, very smart engineer, you cannot do it alone. You will have, because they are very interdisciplinary, so you will need to collaborate. So it requires involvement of different experts and disciplines, and think about multiple design targets. Green wall, not just for energy efficiency, not just for amenity, but also for water treatment. So think of multiple targets, and this will actually impact a lot your design. It will impact the size, it will impact the appearance. So, so think about this. This is a summary table, let's say. It's not a complete, but it's something that we try to, let's say, put together. So for example, you want to, your design target is water quality. Okay, you want to treat water, and then you see, well, I will need expertise in sanitary engineering, in water ecology, in chemical engineering, right? And then you see which nature-based solutions I can use, and then you see here, well, units. These are nature-based solution groups, as I mentioned. So you can use some units, nature-based solution from rainwater management. You can use units, most of them actually, from remediation, treatment, and recovery. You can use vertical greening systems and food and biomass. You can use system units from food and biomass, and then you can check actually in the other tables which are these units that you can use to address water quality. So now suppose you are in a building and your task is to treat gray water, and you decide, well, I will use vertical greening system, vertical wall. But then you can realize that this same unit can also address water quantity. So you will go and check with urban hydrologists how much water you can catch from your roof, for example. And then you see, well, it can address biodiversity, and you will call Ina to ask, well, what can I do to increase biodiversity in this wall? But then, of course, you will ask some architects, some civil engineers, how to build this green wall to actually serve as insulation material. So you see, You start from your water quality problem, but then at the same time, you can address many, many more. And if you put tomatoes or whatever on your wall, you can also address food and biomass production. So this is the idea in the design. So start with something, but then think about other design targets and other experts to provide you with sufficient knowledge to design this nature-based solution in a multi-purpose way. Just to finish, and this is something really from EdiCitNet, how to link food and water targets, for example. So suppose you start with, I want to set up edible solutions in my city. Okay, I want to set up gardens. And I want to set them in these two areas in my cities. Okay, what you see here, red and green, is the different land use. This is really heavily urbanized. This is also a residential area, but you have, and these are some green spaces. But of course, you have different solution also for urbanized areas. You can put up rooftop gardens, for example. So what you need here is to define your scenario, and you need to collect some data. How much area I will dedicate for edible solutions for gardens? How much of this area is actually percentage of impervious area? How much is pervious area, and so on. So you need to collect some data, some precipitation data, and so on. And then you compose your scenario by selecting a food production system, rooftop garden, whatever, simple plots. Then you select your crops. You have to select the sources of water and nutrients. Will this be wastewater? Maybe it will be difficult, but okay, maybe kitchen waste composting. When you think about all these things while setting up your garden, you need to come up with the following results. And this is enabled with some simple models. So first you need to calculate what is your resources demand. Then you need to calculate how much products you will have. And then you need to calculate what will be your environmental benefits. How much, and the environmental benefit is what is the amount of local food, how much rainwater is avoided to sewer system, how much rainwater you will use on your gardens, for example, how much household waste you will use in your gardens instead of ending up to landfills, and so on. So these are the numbers that really help for people to decide how to set up gardens and to decide to set up edible solutions as nature-based solutions or not. And solutions for what? Maybe the edible solutions will be solutions not just for food, but also for waste management. So you can manage the household waste to be used as a fertilizer. You can find, and I'm really sure, as Ina already showed you, you will go to this platform, to the EdiCitNet project, find a lot of things there to learn. And also you will find this platform, and Ignacy and Antonina will help you with that, to join this platform, actually to register and to use all these models, maybe to get some information, where are the gardens, what do they offer, how much resources they use, and so on. And with this, I will conclude. So basically, what I can say, it's about time to start thinking about cities as really formations and structures that are implementing circular metabolism, which means that all these arrows that are coming to the city and all these arrows that were going out of the city are really, really minimized. And only in this way we can say the cities are not burdens to the environment anymore. Then, as we saw, nature-based solutions, by their definition, they can really facilitate this transition from linear to circular, but we have a lot of obstacles And one of the obstacles is actually the existing infrastructure. There are some noises coming. So it's the existing infrastructure. I will just give you one example. We want to use as little water as possible. We saw we have 130 liters per person per day, and we say, well, if we manage to use 50 liters per person per day, that will be great. Well, now as engineer, I have to say that this will not be great. Why not? Because these systems are designed to convey 130 liters per person per day, or 150. What happens if I reduce this? Well, the water will stay longer in the system, and it may happen that it will be bacteriologically compromised. So what do we do? Well, what we do is, whatever changes that we implement, we need to calculate the impacts of this change. But what we can really do in terms of reducing the water need is to implement these solutions in new developments, because they were not planned for these existing systems. And this is something that we can really contribute. So it's just, you know, something contradictory, but that's a fact. I mean, the water will not be so good if we don't use it. All our systems in the cities are constructed, are designed in a way that we use more and more and more. So that's, you know, well, I leave it to your thinking and reasoning. So, so you saw this classification and framework, and I invite you to go to basically these two papers. There are more papers to go through. So here you have the list. They are all downloadable. But the first two, basically you can find these frameworks and descriptions of the nature-based solution units and so on. So you can basically use it in your tasks further on. And with this, I will now really conclude and thank you all.